Okay, the first question, or the next question is question 3, which is this is on the November 2018 paper 2. You're asked to work out the electronic configuration of a bromine atom. Well, to work that out, most of you did this pretty well, but let's just show you something that might make things a little bit easier. You're trying to remember the order of filling of the orbitals and electronic configuration. Just look at your periodic table. So the first row, you know that the first shell only holds, or only has a 1s subshell, no other subshells. So it's 1s. Then over here 2s, which holds 2, 2p, which holds 6 in total. Then 3s is the next subshell, 3p, 4s, 3d, 4p, 5s, and so on and so on and so on. So you can work it out that way if you're struggling a little bit. So going back to our bromine, you correctly, most of you highlighted that it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. We could have got that because it's 4, fourth row, p5. So you should be able to get that relatively straightforwardly. Okay, then you're asked to draw the valence, just the valence shell. So the valence shell is the outermost shell. So we're only looking at the electrons in the fourth shell. So anyone who drew the 3D subshell didn't get the mark, and you should have drawn some variations on this. But there's your 4s down there, and that should have been filled. And then I would have drawn it. Oops, you can draw them all three together, but I'm going to draw them separately like that. There should be 5 in here, something like that. If they were double-headed, that's okay. But that's how you'd have done it. Most of you should have done it. Right, drawing Lewis structures is not easy. There's no doubt about it. It's not straightforward. I'm just going to check if I've got this focus. I'm going to pause. Right, there's a couple of really good videos on how to do this particular ion. So I recommend looking at those. I'm going to get to the point fairly quickly. But the first thing to do is to work out how many electrons in total you've got to find places for. And so you've got to count the valence electrons of bromine, which is 7. Hope you know that. That's what's in group 7. You'd have to tot up the number of valence electrons of oxygen, which is 6 for each oxygen. There are 3 oxygens, so 18. And you have to realise that it's a negative charge, which some of you seem to have missed the point there. So it's an extra 1. So in total there are 26 electrons to find homes for. So the thing to do, we know that or hopefully at least that the bromine is in the middle. And I would start by drawing the electrons around the bromine, and I'm going to draw them as fairly juicy dots. I'm going to draw them all as dots. The IB doesn't mind whether you draw them as dots or crosses or triangles or whatever. Well, dots or crosses, or in fact as bonds, which many of you did, and that's fine as well. I prefer to draw them as dots. You can see what I'm doing. And I might have done this on rough paper to start with. So that's bromine's outer electrons, and then you've got each oxygen. I'm not going to draw an oxygen for you. You have to do that. 6 electrons in the outer shell. So let's start by drawing a bond between oxygen here. We'll draw these as crosses, why not? Just to show you where the electrons have come from. Now, oxygen's got 6 in its outer shell. 1, 2, 3, 4, 5, 6. You don't have to do this for the IB, but I quite like it. But we'll draw the 7th one as a triangle, and the 8th one of this set, if you like. This is the one that's the incoming one that's made this a negative charge, right? And then you've got 3 other places the other 2 oxygens could go. Each oxygen, remember, has got 6 electrons. It needs 2 more to fill the outer shell. So it's going to be what we call a dative bond. I'm going to draw the oxygen electrons as crosses, and show the bond is a dative bond between the bromine and the oxygen. Those 2 bromine electrons are going to fill that gap, and we're going to do the same thing down here. I'm going to squeeze it in a little bit because I've drawn it too big. Again, I'll probably do this on rough paper, so I'm sure. And that many of you thought was the final answer, and I'm going to draw it a different way. It's wrong. There's still something missing. I'm just going to draw it with lines to start with. I prefer it if you did the dative bonds as dative bonds rather than lines, but you're allowed to get away with not doing that. So that's another way you could have drawn this. There we go, like that. But let's not forget to draw the minus charge. That's the extra little detail we mustn't forget. We've got to draw the minus charge around this Lewis structure. Something like that would have got the mark for the first one. If you didn't draw the square brackets, or you had the wrong number of electrons or whatever, you didn't get the mark. You were allowed to draw these as lines rather than arrows though. So that should be all 26 electrons covered. It's worth checking at this point that you have. If you haven't got 26 electrons, start again, go back to your scrap paper. Right, so the one that doesn't follow the octet rule, the whole purpose of this way, or this model of thinking about bonding, is to just to help us understand kind of what the structure might look like really. And I think it leads on to then thinking about resonance structures and the stability of the bromine and so on. There's a way of thinking about these substances, and there's a little bit of thinking, right? So if you look at the formal charge of the bromine here, and it comes up, I was just checking, it comes up in the next question. So the formal charge is the number of valence electrons. This is sort of the bromine, by the way, which is 7. Number of non-bonding electrons in the bromine is 2. The number of bonds it's making, or it's 3. So 7 take away 2 take away 3, which I'm sure you can all work out is plus 2. So the bromine's got a formal charge there of plus 2, and the oxygens all have a formal charge of minus 1. So the alternative ways of drawing it, which don't follow the octet rule, which is allowed for elements, the third row and down, aren't they? It allows us to draw compounds that have got formal charges that are lower, and they're preferred. They're considered to be the more stable way of drawing these things. Right, so if we want to reduce the formal charge on the bromine here, we could imagine taking 2 of these electrons and making that into a double bond. So let's just draw that way first of all. So I'm just going to draw these one at a time. It's going to take a minute, so feel free to fast forward. Leave the lone pair alone. I'm going to leave this one alone as well. That was a bit dark because I chose the one with the minus charge. I'm going to put the minus charge down here now. There it is. And make this a double bond. There we go. So we've now got a double bond in there. And this, provided we've got the square brackets around it and the minus charge, is one of the allowed possible answers. You could have drawn that as a dot or a cross or anything, by the way. But the formal charge on the bromine now would be lower because 7th valence electrons, so I might as well work it out. 7th valence electrons, 1 non-bonding pair, so 2 non-bonding electrons there. Take away the number of bonds it's making, which are now 1, 2, 3, and there's a double bond, so it's 4 in total. So it's 7 take away 2 take away 4, which is now plus 1. So that's reduced the formal charge of the bromine. We can go one step further by drawing this one and this one as double bonds. So I'm just going to quickly sketch those out. Oh dear me, I'm rushing. And now this was another possible allowed answer. So both of these would have got the mark actually, because both of them are possible answers. But this one's got a formal charge now of 7. Take away the 7 valence electrons. Take away 2. Take away the 1, 2, 3, 4, 5 bonds it's making. And this has now got a formal charge. The bromine, that is, of 0. The formal charges of the oxygens will be 0, 0, and minus 1. Some of you attempted to draw the bromine with some of you tried to draw the bromate with 3 double bonds between the bromines and the oxygens. You can't do that because you have to have a minus charge on the oxygen. Oxygen being more electronegative than bromine, the minus charge would be on there, so you can't draw that as the double bond. Anyway, this has got the lowest formal charge, so job done. And I've already answered this question on the previous part, but very briefly. For structure 1, the formal charge on the bromine is referring to the bromine is +2, for the reasons I've worked out just a moment ago. And you had to, for the first mark, also say what the formal charge on the other structure that you drew was, which is either 0 or 1. And so, which is the preferred structure? And the answer is structure 2 is preferred because it has the formal charge close to 0. And there are all sorts of variations on that answer, which I wasn't allowing. I wanted you to get exactly what it's saying there, okay, because that's what the marks are for. Okay, now if you're asked about the geometry of the ion, or the molecule in some cases, please don't give the electron domain geometry. Give the geometry of the substance itself. Right, so you've got to look back at your structure. We've got each bromine is joined in whichever of the structures you've drawn. In every single one of them, you've got bromine joined to 3 oxygens, and you've got 1 lone pair. So it's just like any other substance. I'll give you another example with 3 bonding domains and 1 non-bonding domain, so something like ammonia, and you should just know that that's trigonal pyramidal. And I have to say to you, this is an example of you've either learned and revised this stuff, or you haven't. I suppose some of you got that wrong, maybe because you got the structures wrong. But there we go, trigonal pyramidal for the anything with 3 bonding pairs and 1 lone pair. And then the reason, I understand some of the sort of weird and wonderful answers you might have given about the reasons, but all you have to say is what I've just said, which is 3 bonding pairs and 1 lone pair or 1 non-bonding pair. Even, I'm just reading now, you get the mark for saying 4 electron domains. So if you said that and I didn't give you the mark, come back and see me and I'll think about it. The bond angle in trigonal planar is 107. Well, that's the value that I've taught you. You were allowed anything, well, a slightly wider range than that, but I've taught you 107. I expected you to write 107. The reduction, right? This is a half equation question. This stuff should be absolutely routine, and I was kind of grumpy when marking this, I must admit. So few of you could do it. This is an absolutely routine. Given I told you redox standard level stuff would be in the assessment, you should have been able to draw a half equation. So I'm going to remind you of the approach. You're told you start with bromate 3 ions, and some of you didn't even use bromate 3 ions, even though you were told what they were in the question up at the start of question 3 there. But bromate ions act as oxidizing agents. In other words, they get reduced from 5 to something else, where you're told to go to bromide ions. There you go. So it goes from there to there. The first thing you do is to check the number of the element that's changing. Oxidation number is the same, which they are. We've got 1 bromine on each side, and then you balance the oxygens with water. And I hear some of you now going, "Oh yeah, I remember how to do this now." Once you've got the oxygens in place using the water, we've got to balance the hydrogens using H+. You're told as acidic conditions, so there's a little clue what you're doing there. And then now all the elements are nicely balanced. You've got to balance the charges with electrons. The total charge on the left hand side is +5, so from the 6 H pluses and the 1 minus, and the total charge on the right hand side is -1. Difference between those is -6, so we always add the electrons to the more positive side, remember, and that's your answer. You should really put aqueous, aqueous, aqueous and liquid there. So that was that one. Absolutely routine. Another way of checking, by the way, this has gone from bromate 5 down to bromide -1, so it should be a 6 electron change. Many of you drew a reaction without any electrons in at all, which was a bit upsetting. The next question tells you that you're using the bromate 5 to oxidize iron 2 to iron 3. So you have to write the redox reaction, right? Not the half equation, but the overall ionic equation. So iron 2 goes to iron 3 using this half equation. To combine them, you've just got to make sure you've got the substitute. I'll bring this over here so you can see what I'm talking about. Hopefully you can see it. Move it so you can fold this up. There's the two half equations. Just got to combine them so you've got the same number of electrons on each side. So you must multiply this entire thing by 6 and then cancel the electrons. That's all you have to do. This was a disastrous question for just about everybody, unfortunately. So you've got 1 bromate ion, 6 hydrogen ions. The electrons will cancel, so we never bother drawing those. We've got to times the number of iron 2s by 6. And then we've got, that goes to a bromide ion, 3 waters, and 6 of these. And that's your ionic equation. Just worth checking that it's right. Maybe this is the sort of thing you do on rough paper before you're sticking it straight on the paper. That's absolutely fine. That should have been done better. The next question you haven't done yet, so you can skip past this if you want to for now. But what you'll be using is working out the E cell or E standard for this particular reaction, and which you work out, as we'll soon learn, by finding out the E standard for the reduction, take away the E standard for the oxidation, and the E standard is this value given in the question, which is plus 1.44. The other one you'd have to look up, and it's in the data book as plus 0.77, so it's 0.44 take away 0.77, and that gives you 0.6 plus 0.67 volts. And then again, we've not done this yet, but delta G is equal to minus NF. E standard, that's this value here. That's a constant, which is 96,500 coulombs per mole, and that's the number of electrons transferred in this reaction, which is 6. So it's 6 times 96,500 times by the voltage, or the E standard, or the EMF I should say, and that comes to minus 3.9 times 10 to the 5 joules. Don't need to worry about that at all. That's not in the new syllabus, so we can forget that. We'll stop there.